Welcome back to the Math Professors. If you enjoy content that can be found in a college math class, please consider liking, subscribing, and sharing. I'm Professor Van Hamlin. I'm going to cover norm space. So we're going to talk really about length and the norm of a vector. So the length, the norm, or the magnitude of a vector v, which is v1, v2, all the way up to vn, so that vector is going to be an Rn, is given by this. So this is the magnitude of v, or the norm of v, or the length of v, is going to be the square root of v1 squared plus v2 squared all the way up to the addition of vn squared. So it's the sum of the components squared all underneath the radical, which really is just an expansion of our distance formula into Rn that was given in a previous video. So given the vector u, find its length. So I'm going to do a vector in R4, and then I'm going to do a vector in R2, and then show you how similar they are. So if I want to find, say, the magnitude of u here, the length of u, it's going to be the square root of the sum of the squares of its components. So 2 squared plus 0 squared, these parentheses are quite redundant when they're not negative, plus, I could have said, what I mean by that is just 3 squared. I could drop the parentheses on these two because it's positive, but just to stay consistent, I guess I'll put parentheses around that. Okay, so then this is going to be, 2 times 2 are 4, plus 0, plus 25, plus 9. So what we get is we get the square root of 38. Now, if I want to find the length of a vector in R2, it's done the exact same way. It's the square root of the sum of its components squared. So this is going to be 8 squared plus 6 squared, which is going to be equal to the square root of 64 plus 36, which in this case is going to be equal to the square root of 100, or 10. Okay. Now here I put a special vector here that where the components are both divisible by they're both even. So what I want to show you is there's a quick property that says the length of a scalar multiple. So what is the length of c times v? So what we're trying to say is the magnitude of a scalar times a vector is going to be equal to the absolute value of that scalar multiplied by the length of that vector. And we can see this here. I want to show you with this property. I wish I'd have made them both negative just to kind of show you this. So let's do that. What if these things were negative? Would that really change the length of this vector? Well, this would be now a negative 8 squared. This would be a negative 6 squared. So we still got a length of 10. So we can really see the length of a vector, 8, 6, and the length of a vector negative 8, 6. Of course, they're going to have the same length because they have their same magnitude, because it's the sum of the squares of its components, which makes under the radical always positive. So this is divisible by negative 2. So I can say that u is equal to negative 2 times 4, 3. So if I want to find the magnitude of say, u here, well, this is going to be equal to the magnitude of this. And what we know is that this is going to be the absolute value of negative 2, because that's a scalar, multiplied by the magnitude of 4, 3. And the magnitude of 4, 3 can be done the exact same way that we had here. So this is going to be equal to the absolute value of negative 2, the square root of 4 squared plus 3 squared. So this would be 16 plus 9 to the square root of 25. So the absolute value of negative 2 is 2. Square root of 25 is 5, which still gives us a length of 10. Really just verifying that this property works, because it's the same length as just doing it to the original components. So with this property, we can also discuss what's considered a unit vector, because it's just a scalar times another vector. So how do I make a vector of length 1 is really what we're trying to pull off. So the unit vector becomes useful, like especially in a Calc 3 class. If v is a non-zero vector in Rn, then the vector u, which is defined by v divided by the magnitude of v, has length 1 and is in the same direction as v. Now, really note that this is nothing more than 1 over the magnitude of v, multiplied by v. So really what we have is we just have a scalar multiplied by a vector. Now, if v has, magnitude v, then I can prove that the magnitude of this thing would be essentially the absolute value of this piece multiplied by the magnitude of v. Now, since the magnitude of v is going to be a positive length, then the absolute value of this first part is just going to be, 1 over the magnitude of v multiplied by the length of this, which is the magnitude of v. So the magnitude of this blue thing is just going to have length 1. Showing that is this. So what is the magnitude of 1 over the magnitude of v times v? Well, again, this is nothing more than a scalar, so this would be the absolute value of that multiplied by the magnitude of v. And since the magnitude is already positive, this is redundant. This is just 1 over the magnitude of v multiplied by the magnitude of v, which would be equal to the magnitude of v over the magnitude of v, which in this case will be equal to 1. So I can tell that the length of this has length 1. Okay, so let's find some unit vectors. And it's going to be in the same direction because it's it's a scalar times a vector. So when you take a scalar times a vector, all you do is just stretch or squish or stretch the thing. So let's figure out this thing's length so that I can find this unit vector. So in order to start this, we have to first find the magnitude of v. Well, this is going to be the square root of the sum of the squares of its components. So 25 plus 4 plus 1 is going to be the square root of 30. So that means unit vector u, call it just u for unit vector, is going to be, that vector divided by its length. Now, this is nothing more than, 1 over root 30 multiplied by that vector. So if you want to, we can put that 1 over root 30 in every one of those components. And then what we could prove is the length of this thing is 1. So if you took the square root of the sum of the squares of these components, you will get 1 back. That is guaranteed. So let's find it for this one. So what is the magnitude of v? Well, this is the square root of 4 squared plus 3 squared, so 16 plus 9, which is square root of 25, which in this case is going to be equal to 5. So since u is equal to v over the magnitude of v, this is going to be 3 all over 5, or I can say 4 over 5, and this will be 3 over 5. And again, we could prove this. What is the magnitude of u? We'll do it with the easier one because it'll be quicker. Well, this is going to be the square root of the sum of the squares of its components. So I'm going to have 4 over 5 squared plus 3 over 5 squared. So this is going to be the square root of 16 over 25 plus 9 over 25, which would be the square root of 25 over 25, which indeed is just 1, like we said. So this is the unit vector of this in the same exact direction. So geometrically, what we have here is this is 1, 2, 3, 4, 1, 2, 3. So our vector v is that. That would be this vector. And then if I wanted vector u, which is going to be the unit vector in its direction, well, I have to go 4/5 this way and 3/5 this way. So you can see it's about there. And that blue thing is going to have, this vector here, which is this, will have length 1, but it'll be in that particular direction, in the same direction as v. So the distance between two vectors in R2, and what I've done is I've drawn a u vector, which is u1, u2, and a v vector, which is v1, v2. And the distance is really going to be nothing more than the length of this that line that goes from v1, v2 to u1, u2, or backwards, it doesn't really matter. And the reason why is because distance formula says it's a square root of the sum of the squares of these differences. So either u1 minus v1, or v1 minus u1, or u2 minus v2, or v2 minus u2. It doesn't matter the order of this subtraction because you're going to square them. So changing the order is only going to change the sign, but it won't change the square because it'll always become positive. So really, I want to show you is that the distance between any vectors in Rn is nothing more than, you can see that this looks like a magnitude. This is actually the magnitude of the difference of these two vectors. So we'd say that the distance between any u and v is equal to the magnitude of u minus v, and that's what we have. This is nothing more than the vector, u minus v, or it could be the vector v minus u, just going the other direction, but it doesn't matter because I'm going to take its magnitude, so the length of a vector in one direction is the same as the length of the vector in the other direction. So that's why this is equal to the distance of u minus v, or you can say v minus u, it's up to you. So I have some properties. A property I just kind of discussed. So first, distance between u and v is always greater than or equal to 0. So one thing you could say is the distance from my house to work is the same thing as the distance is always going to be positive, because the distance from my work to my house is always considered that positive distance. And the reason why is you have the square root of the sum of squares. So the smallest that can be underneath this radical is if these two things are the same, which would be 0. So the smallest it could be is the square root of 0, which would be 0. But otherwise, these things will be non-negative, so they'll either be 0 or bigger, which means it's always going to be greater than or equal to 0. 2, kind of talking about what happens if it is 0. Well, if the distance between u and v is 0, this only happens if and only if vector u, is equal to vector v. I should have vector signs on top of all these, but I get a little complacent. And then finally, the distance from my house to work is the same thing as the distance from my work to my house. So it doesn't matter the order in which you do these things. That is also true. So what I want to do is I want to compute the distance between u and v. So u is in R5, v is in R5, so we can actually compute the distance between these 5-dimensional vectors. So what I first have to do is I first have to find u minus v. Well, u minus v is going to be equal to, well, subtracting the components, this is 4 minus 5, this is 1 minus 0, minus 3 minus 2, 0 minus 1, and then finally 4 minus 4. So what we're going to get is the vector negative 1, 1, minus 5, negative 1, and 0. So if I want to find the length of this vector, well, we know that the distance between u and v is going to be the magnitude of u minus v. So this is going to be the square root of the sum of the squares of these components. So negative 1 squared plus 1 squared plus minus 5 squared plus minus 1 squared plus 0 squared. And what we're going to get is the square root of 1 plus 1 plus 25 plus 1 plus 0. So this is going to be equal to the square root of 28. So what I find interesting is we're not just stuck at R2 or R1 or R3. This expands to a countably infinite amount of dimensions. So just because you can't see it doesn't mean we can't compute these lengths and distances. It's super cool, math's ability to extend. So the dot product at Rn. So let u be u1 all the way up to un, and v be v1 all the way up to vn. Then the dot product, or the scalar product, u dot v is u1 v1 plus u2 v2 all the way to un vn, and we've discussed this previously. So what I do is I want to compute the dot product of these two R4 vectors. So u dot v is equal to, well, it's going to be 3 times 1 plus negative 1 times 4 plus 0 times negative 3 plus 5 times negative 1. So it's a sum of the products of the components. So this will be equal to 3 minus 4 plus 0 minus 5. So this dot product is going to be equal to negative 6. So properties of the dot product. So if u, v, and w are vectors in Rn and c is a scalar, then the dot product is commutative. So u dot v is equal to the product v dot u. It's distributive. U dot v plus w is u dot v plus u dot w. When you multiply these three things together, knowing that this is a scalar times this dot product, well, it's going to be the scalar times the first dot the second, or it's going to be the first dot the scalar times the second. So again, we can see that when you multiply, you only do two at a time. So I can either multiply c by the first, or I can multiply c by the second, and then do that dot product last. A really important rule is the dot product of v and itself is the magnitude of v squared, and we're going to use that to our advantage very soon. And v dot v is always going to be greater than or equal to 0. And if v dot v is equal to 0, that means v has to be equal to 0. So I'm not saying that the dot product is always positive, but it's always if it's the dot product with itself. So we can kind of see these rules here, that if u dot v is equal to v dot u, if I switch these components around, if I said what about v dot u instead, well, it's now first component of the second, second component of the second component of the first, and then similarly 3 times 0, and then I have negative 1 times 5. And all that is done is just rearrange each one of these products in the other order, and since multiplication itself is commutative, this will still be equal to negative 6. So it's really taking advantage of the commutativity of multiplication. The distributive property, we might show an example later. If I did v dot v, we can always guarantee that v dot v is equal to 0. Let's just use this v that we have right now and then kind of verify it. Well, if I take this product, this 1 times 1 plus 4 times 4 plus negative 3 times negative 3 plus negative 1 times negative 1, well, what we can see is all we're doing is the sum of the squares of its components. So this is 1 squared plus 16 plus 9 plus 1 since I'm essentially, well, let's do it this way. Let me write it this way. This is actually 1 squared plus 4 squared plus minus 3 squared plus minus 1 squared. And when you square these things, they will always be non-negative. So that's why it's always greater than or equal to 0. So 1 plus 16 plus 9 plus 1. So this is kind of recognizable right here. We've been practicing the sum of the squares of components, and what that means is v dot v is equal to the magnitude of v. So more importantly, from this particular property, I could solve that for the magnitude of v, and we can say that the magnitude of v is nothing more than, well, if I want to isolate this, I have to square root this. So this is going to be the square root of v dot v. Now, what I love about this is magnitude is kind of akin to like an absolute value. It's, absolute value is the length of one-dimensional things, essentially. And this shows like the absolute value of this is equal to the square root of the square of the component. Now, we don't write a square when it comes to dot product because it's a slightly different kind of product than just multiplication. But it still has that same feel, that v dot v, which is close to the idea of v squared. So I have the square root of something squared being equal to the absolute value of that particular thing. So the magnitude of v squared is actually the square root of the dot product of v and v. So let's take this and kind of explain what we can use to re-identify So our last thing is going to be talking about the angle. So here's our last example, and really we want to talk about the angle between two vectors. So the angle theta between two non-zero vectors in Rn is given by the cosine of theta, which is u dot v over the magnitude of u, magnitude of v, and nothing more than just an extension of the law of cosines into angles. I'll make a video proving it someday. So if u is equal to this R4 vector and v is also equal to this R4 vector, well, now we know how to compute a whole bunch of things. I can compute u dot v. Well, u dot v is going to be equal to 1 times minus 3 plus, minus 4 times 2 plus 3 times 0 plus 0 times 1. So u dot v is going to be minus 3 minus 8 plus 0 plus 0. So this gives us negative 11. B, I want to find the magnitude of u. Well, the magnitude of u is nothing more than the square root of u dot u. So this is u dot u. So this is going to be equal to the square root of, the product of all its components squared. So 1 times 1 minus 4 times minus 4. So I'm just going to write them as we did before. So plus minus 4 squared plus 3 squared plus 0 squared. So this is going to be equal to the square root of 1 plus 16 plus 9, which is equal to the square root of 26. Now, C, a lot of room. If I want the magnitude of V, well, this is going to be the square root of V dot V. So this is going to be the square root of the squares of its components. So minus 3 squared plus 2 squared plus 0 squared plus 1 squared. Onto that radical, so this is going to be equal to the square root of 9 plus 4 plus 0 plus 1. So this is going to be the square root of 14. D, if I want the distance between two vectors, well, the distance between two vectors we already know is the magnitude. This was equal to the magnitude of u minus v. Now, since this is a magnitude, I could also write it as the square root of the dot product of u minus v with itself, u minus v. So again, we can see that the magnitude is very much related to a dot product. So what I'd have to do is first start out with what is, u minus v equal to. So when we do this u minus v, we have to subtract the common component. So u minus v is going to be 1 minus a minus 3 minus 4 minus 2. 3 subtract 0, and finally 0 minus 1. So u minus v is going to be equal to 4, negative 6, 3, negative 1. So what we know is that the distance between the two vectors, so kind of start that with this again, so I have a nice notation. The distance between two vectors, which is the norm or the length of the subtraction, is going to be equal to the square root of, this u minus v. So 4 squared minus 6 squared, 3 squared, negative 1 squared, onto the radical. So we're going to have square root of 16 plus 36 plus 9 plus 1. So 10, 46, 56, and 6 is 62. So this would be root 62. Now the last thing we're going to do is find the angle between these, and what we know is through the law of cosines, we get this formula. So then I know that the cosine of theta is equal to, well, we know it's u dot v, and we've already calculated that's negative 11, divided by the magnitude of u, the scalar of root 26, multiplied by the magnitude of v, which is the scalar root 14. So then theta will be equal to the cosine inverse of the right-hand side. Now it's up to you if you want to put this in radians or degrees. Ask your teacher. It doesn't really matter to me as long as you label it. So mode, I am in a radian, so when I put this in here, we have second cosine inverse, negative 11 divided by second square root of 26 times 14. So I get 2.19 radians. Or if I want to put this in degrees, change the mode to degrees, we get 125.2 degrees. So the underlying idea is we get geometry, we get lengths, distances, and angles all described through this interesting product here, through this dot product. So our next lecture, we're going to talk about a general inner product where we generalize this idea, and then we can redefine the geometry of space. So if you like the content, please subscribe.